So today we are going to discuss the Maslov index. Um, so we know that we have proved that the operator df from wkq of f of with values in E to wk minus 1q sigma of the tangent with values in the differential form, and df star, which is operator from wkqf with values in the differential form to wk minus 1q sigma with values in E are Fredholm operators. So we can consider so we can talk about the Fredholm index. But a problem is that once even if we know about the Fredholm index is well defined, we need to compute the Fredholm index. So a direct way is that we need to determine the kernel of df and the co-kernel of df, which is we have proved that it is isomorphic to the kernel of df star. So in this case, we need to solve elliptic equations. But we know that here we are dealing with a very general case that, or even in the special cases, they are hard to prove. So for example, when sigma is the space is sphere, that is CP1 as a Riemann surface, then we know that df and we take df to be the standard d-bar operator on sigma, and ef and E to be just the tangent bundle. I think it should be the tangent line bundle, or so let E be some bundle. So let E be a trivial bundle. Then we know that d bar U is 0 if and only if U is holomorphic. In this case, we can determine easily because U is homomorphic, then we will have U is, then by Liouville theorem, we will know that the kernel of df is just the space of all complex numbers. So it is of dimension 1. Of complex dimension 1 and real dimension 2. And the general case, we should use the Riemann-Roch theorem. That is, we use the genus, that is, we relate the space of all homomorphic sections of some line bundle OD, or to say LD, to the genus of the Riemann surface and the degree of the line bundle. And we know that this is the first Chern class of the corresponding line bundle. So here we also need to develop a theory concerning the topological invariant to the bundle pairs. That is, we need to assign one bundle pair to to some values in R. I think it should be in Z, in the space of integers. And here we use the so-called Maslov index. It is first introduced by Maslov. In like 1965 or 1966 or so, and in any cases we will cite a note paper because in 1967 that he proves he related the Maslov index to intersections. I think it should be say he relates the Maslov index to the topological invariant like H1 of the space of Grassmannians, that is L, V, and with values in Z. And the Maslov index mu is then given as the pair with the where gamma is a curve in a space of all Lagrangian Grassmannians. So once he relates this, then and then Viterbo in 1987 applies. I think it is 1987 or 1984 or 1987. Okay, so it is a French paper called I don't know about the exact. I forgot the exact time. Yes, 1987. Yes. In the dash sections of like so applies Maslov index to the Lagrangian intersection. Lagrangian intersections. So then we were concerning the intersection of two Lagrangians, and we assigned an index to the two points. That is, if it's x or y, then we assign the index mu xy to this pair of points. And at the same time, or to say a little earlier, that is Conley and Zender. They developed an index for the Hamiltonian theory. It is called the Conley-Zender index. And they are also originates from the Maslov index. And Salomon and Robin and Salomon in 1993, 1990. Robin and Salomon in 1990, I guess 1993. So they give like systematic approach, or to say a systematic treatment to the Maslov index. And roughly speaking, we are treating with the Lagrangian Grassmannian. So the first definition is Maslov Grassmannian, the Lagrangian Grassmannian. So we let V omega a symplectic space, symplectic vector space of dimension 2n. And to say the Lagrangian Grassmannian is a subspace of the Grassmannian, and we write it as LV is a space of all Lagrangian subspaces. So it will be the subspace of the Grassmannian of all n-dimensional subspaces of V, and with some effort we can know that it is compact. On the other hand, we have also if we could assign V to a complex structure, so it is a symplectic, it is a complex vector space of complex dimension n, and we have the space of our totally real subbundles, like we write R. No, subspaces. That is, totally real subspace means that a subspace F such that JF is F itself. So, no. JF is orthogonal to F. So just like in a complex plane C, the real axis R and is the corresponding and the imaginary axis IR are all totally real subspaces. And in fact, in this case, any line is a totally real subspace. Any line through the any one-dimensional subspace are totally real. So what I'm going to say? Yeah, so we want to define the Maslov index, and roughly speaking, the Maslov index mu is a map from the fundamental groupoid to the half integers. That is, we have any curve gamma, which is 0, 1 to LV, connecting to Lagrangian subspaces. Then we will assign a half integer mu gamma. So we know that when we are considering loops, that is, we will obtain h1 of LV with values in Z to integers. That is a loop gamma, and it map into mu gamma, because we know that a loop consists of, if we pick 2 points, then the first connects this point to that point, and it gives a half integer, and then we go back and we give another half integer, and we sum them together, then we will get a integer. It is like a double of it is like a double of this one path. So but the explicit definition needs some trick, like like in Arnold's paper, in Arnold's original paper, it is something like we are considering, so let's pick L0 in LVB1 Lagrangian subspace, like we can regard it as, because when we pick another frame, we will regard it as the space of Rn in the symplectic vector space R2n. And we know that in this case, given any curve gamma from S1 to LV, then we will obtain yes. So let us write this as LV and with a reference plane V0. Then we have the projection V to V0. That is just via the natural map R2n to Rn cross 0. So we just omit the other n variables, and then we get yes, and then we have the kernel and the image. The image is just the intersection of V with V0, and the kernel is like if we have one such Lagrangian, and this is another, and this is just the symplectic dual of L0. No, it is not symplectic dual. It is if we could pick a metric, since we have V omega, when omega is a symplectic vector space, then by linear algebra we know that there is a J compatible with omega, so that V becomes a unitary space. That is, we repeat G equals to omega and JV. GVW equals to omega of V and JW. Then G is a positive definite to form. And then it becomes a unitary space. So we can talk about, for space L, we can talk about the dual of L. And so when this is L0 and this is a dual of L0, and any plane, that is any plane will have two intersections. One is on the space L0, that is the image at the intersection, and the other one is the projection onto the line. So kernel is the projection onto the orthogonal. Orthogonal space. And we say that so because the dimension of the Lagrangian subspace is half the dimension of the original symplectic space, we know that in generic cases, we have just V intersect with V0. No, I mean L intersect with L0. Is trivial. So that is, they are transversal. And then there will be some cases when the L intersect with L0 is non-zero. So they are not transversal. And we just pick So why we say it is generic? Because it is an open and dense subset. In the Lagrangian Grassmannian, and this will be closed. So so this will give a closed subset, which is we denoted by lambda 1 of L0. That is and it should be lambda L0, and we can also stratify it into okay. So and we can further stratify into different dimensions, where we say that lambda 1 is that the dimension of the intersection is 1, and 2, 3, 4, like that. And we know that in this case, the codimension of lambda 1, I think it should not be, say, the codimension of lambda. Yes, the codimension of lambda 1 is 1. This can be easily seen from the definition. So this tells us that when we are, no, it is 2. Yeah, it is 2. So this tells us that once we have this stratification, we know that lambda 1. And when we are considering homotopy classes, we can add the whole the closure to lambda 1, and the closure is just lambda 2 union lambda 3, and so on. So this is so this will define the class in H of we know the dimension of the Lagrangian Grassmannian is what? It should be I forgot that. So let us write n. So it should be n minus 1, n minus 2, yeah, n minus 1. The codimension is 1. So it is n minus 1 of the Lagrangian Grassmannian, and with values in Z. And then we pick the Poincare dual to obtain a class alpha, which is that in H1 of the Lagrangian Grassmannian with values in Z. And this is called a Maslov class. So any curve gamma which is in H1 corresponds to Maslov corresponds to a Maslov index gamma nu gamma, which is the intersection of gamma with the space of all it is a space of transversal, and it is a boundary which is actually a complement, which is the space of lambda L0, and any curve gamma will go from here. Like if we then end from here, it is like so. So we have an intersection of the curve with the space of non-transversal Lagrangian spaces to L0. Then we have the intersection points. So, and we just count the intersection number of the curve with this with this stratified space. Then we will get the then we will get the invariant. And it turns out that mu is an isomorphism from H1 to Z. So gamma 1 and gamma 2 has the same Maslov index if and only if they are homotopic to each other. So this is the original definition of the Maslov index that Arnold and that Arnold uses. But here we will use a more like a convenient case so that we can also consider the similar Maslov index on RV. The reason is that here we are not considering the space of all symplectic vector. We are not considering symplectic vector bundles. We are considering the complex vector bundles or the bundle pairs, which is a pair consisting of one complex vector bundle with the totally real subbundle. So we are going to consider RV instead of LV. So you know that yeah. So let's consider there is a proposition which says that LV is in fact a homogeneous space consisting of the space of the group is a quotient of the group of all symplectic transforms of V, and we impose the symplectic form omega and quotient by GLNR. And the space of all totally real subbundles of V and with complex structure J is the space of all GL of V with complex structure J quotient by GLNR. Okay, it should be yes, so from that case should be true of yes, it is this, and when k is 1, we know that it is 1. Yeah, because the codimension is just like okay, 1992. Okay, 1992. Where? Oh yes, yeah, this is 1992. Okay, so we have the two realizations of these spaces as homogeneous space, and we know that this is because when we impose the almost complex structure J becomes a unitary space, and then we can consider the unitary group acting on V. So we will have it is a unitary group of the space quotient by the orthogonal group, because we know that the G equals which is equal to omega and impose the almost complex structure J, it will be an inner product in any Lagrangian subspace L. So in this case, we are considering, and if we consider the space of a unitary groups quotient by On, then we will obtain the, and we know that SP V omega deformation retracts onto the unitary group. And I think you can find it in Hall using polar decomposition. So this will give us we know that there is a natural determinant which maps U V omega J to the group of to S1. And then when we want to now want to pass through the quotient, we know that for elements A in O1, so determinant of A should be the same. So A1, A2. No, I think we add this to know that this is the thing that we pass to the quotient. But we know that if we have, but we know that determinant A1 cannot equal to determinant of A2, because in these cases, determinant of AI is plus and minus 1. So there will be a sign that is it is equal to plus and minus of determinant of A2. So we must pass to plus and minus 1, and we obtain again S2. But here we do not obtain again S1, but here we cannot distinguish them. So we instead consider the original, we modify the determinant to consider determinant squared, so that they will map naturally into S1 quotient by plus and minus 1, because determinant squared will, yes. So it is just like determinant. Determinant square is just like first take determinant and then take the square. So this will naturally map S1 to S1 quotient by plus and minus 1. So we consider the determinant squared, then this will descend into the homogeneous space. And we know that in this case, GLV3 is also deformation retracts into U with the same reason. So we will obtain a similar map from Rn to S1. And moreover, we know that Rn is in fact deformation retracts onto Ln, which is equal to a unitary group. Quotient by orthogonal group. So why it is a deformation retract, I think we know that by polar decomposition, GL is deformation. GL deformation retracts into so GL deformation retracts into GL deformation retracts onto the space of all unitary groups. And we know that GL of the real number GLNR also deformation retracts onto the space of orthogonal groups. So we will obtain that the quotient also deformation retracts onto the quotient. So we know that Rn deformation retracts onto Ln, and the determinant squared will give the Maslov class. That is the following theorem. So the determinant squared, which maps we write star to denote it is pass to the homology group, which maps H1 of Ln J onto J. I think it should be pi 1. And in fact, they are the same. We know once we know that pi 1 is it is a homogeneous space, so pi 1 is isomorphic to L1, so we just consider pi 1 is as an isomorphism. So we know that mu of gamma is equal to determinant of square star of gamma. We know that because we have seen that. No, we don't have seen that, but we are. So in Arnold's case, they are isomorphisms, and here, because determinant square also gives that an isomorphism, so they are the same. So we know that this in fact gives a classical Maslov index. In order to say this, we need to we have some more work. So we know that determinant is a function from un to S1. So this will give a map determinant star from pi 1 of un to S1 to pi 1 of S1, which is Z. And we know that there is a natural, this is a group homomorphism, and it is surjective in a very, so you can easily see that it is surjective. So then we know that the fiber of this determinant will be the fiber will be SUN. So so we obtain the long exact sequence on homotopy groups, that is pi 2 of S1 to pi 1 of SUN to pi 1 of UN with determinant squared, with determinant start to pi 1 of S1 and to pi 0 of SUN. We know this is trivial, and this is trivial. So this gives an exact sequence that is 0, and this is 0. So this gives an exact sequence of homotopy groups, of fundamental groups, with the determinant star. But we need to pass to the so we're going to say yes. And similarly, we have determinant squared, which maps UN to S1. And it is also surjective because we just because A square is surjective on S1, but with two fibers. So this will give the double cover of SUN to UN to S1 with determinant squared, and this gives another similar exact sequence on homotopy groups. No, I think this is not 0, but we have to impose another 2. Yes, so we obtain this exact sequence, and we know that once we and we know that since SUN has what I'm going to say. So we know that SUN is the so yes, so we know that this is an isomorphism. In fact, although we have although we cannot see directly from this sequence, but we can see that it's an isomorphism. And so we know that this is trivial. And any two-fold covering, that is any J2 fiber of SUN is trivial over fiber bundle over SUN is trivial because its fundamental group is trivial. So this gives us the two-fold covering of SUN is just SUN cross J2, J quotient by 2. So as topological spaces, or as manifolds, not as groups. So we know that this will be Z2, Z quotient by 2, and this is isomorphic to pi 1 of SUN. But we need to pass the determinant squared to the quotient Ln. So we need another sequence that characterizes Ln, that is the fiber bundle On to Un and to Ln, which gives a long exact sequence of homotopy groups. The fiber sequence, it is like pi 1 of On, pi 2 of Ln, to pi 1 of On, to pi 1 of Un, and to pi 1 of Ln, and to pi 0 of On, and to 0, because 0 is pi 0 of Un, which is connected, so its fundamental group is trivial. But we know that pi 1 On is equal to pi 1 SON, and it is a well-known fact that it is isomorphic to Z quotient by 2 when n is greater than or equal to 3, and when n is equal to 2, it is just the group of integers, and n is 1 is trivial because the group itself is trivial. So when n is greater than 3, we know that pi 1 of SON to pi 1 of UN, it should be trivial. Because we cannot map a Z quotient by 2 into a group of integers, and because it is torsion free, so there will be no space for torsions, and so it should be trivial. So we obtain, in fact, it is UN to pi 1 of Ln to pi 0 of On to 0 exact. But we still don't know that if it is but we still don't know if they if L what I'm going to say yeah, so but we still don't know that if it is determinant squared. No, where is determinant squared? But we still don't know the fundamental group of pi 1, and we only know that it is an extension of Z and Z quotient by 2, and there are many possibilities. So we still need another. So we still need some methods, like so we know that there is another sequence concerning concerning S1. That is what we have obtained before. Here, yeah. But this is trivial, and we know that this is also trivial. So this gives in Z sequence, and we know that this is when we pick this to be identity, and this to be determinant square star. No, it is yeah, and this is the just identity. No, I think it is the inverse map induced by projection. No. Yes, inverse map defined by projection. That is because we know that SUN to SON is a twofold covering. No, it is universal. No, what I'm going to say. Yeah, SUN is a twofold covering of SON. Is it right? No. But Yeah, this is a twofold covering, and then we know that we have a natural projection, but the projection will map kinetic components to the same to uh, but the projection is an isomorphism, and in fact we know that they are commutative diagram because they come from a commutative diagram of groups. So and we can inverse the arrow because it is an isomorphism. We can inverse the arrow and we get this is isomorphism and this is isomorphism. So 5 lemma tells us that determinant star square is an isomorphism. This proves the claim because then we know that determinant star square maps pi 1 ln to s1, pi 1 s1, and it is equal to pi 1 of Rn, and via the same map to pi 1 of s1, and also pi 1, yes. So we know that determinant star squared serves as the Maslov index. But now we are going to generalize to bundle pairs EF over the Riemann surface sigma with boundary, or over the compact Riemann surface with boundary. So we know that if sigma is a compact Riemann surface, then it has a homotopy type of a bunch of circles. I think this can be seen from the fact that it's a boundary circle. So we have mentioned it in the first talk. So then it will and we know that the bundle pair EF consists of complex vector space V, and F is totally real subbundle on the boundary d sigma, and we write it as lambda, which is a wedge of no, I think it should be a map from the disjoint union of circles to sigma. It is a map. So we know that lambda gives map lambda, still denoted by lambda, which is map from the disjoint union of bunch of circles to Rn. Because on circles we can always trivialize the complex vector bundle, and then any S1 gives a loop of totally real subspaces. So we have a map from the disjoint union of circles to Rn, and this gives a homotopy class. Lambda star maps, so this gives a class or a number, which is just like if we write this is 1 to n, and lambda I is just the ith circle into Rn, and then we have the number that is the sum I equals to 1 to n of all these loops, the Maslov index of all these loops. So we tell this the boundary Maslov index of sigma. And when this sigma is empty, we just set it to be and it is equal to mu of EF. We just set it to be 2 times the first term number of E. So it will coincide with our original definition of so it will coincide with the classical version of Riemann-Roch theorem, but there are more there are more reasons, because we will see that for example, like on a sphere, Riemann sphere, we can decompose it into a union of two disks, that is D2 plus and D2 minus, and we can compute the Maslov index of D2 plus, because if we have E and we assign to EF, E1 F1 and E2 F2, so we will have the mu of E1 F1 and the mu of E2 F2. And when we glue them together, we will get with orientations mu E1 F1 and plus or minus. I think this plus, but we should no, it is minus. So when we plus them together, then we get a formal sum, because they do not sum to something that makes sense, because there will be no boundaries, and then this will equal to the second to twice of the first term number of E. So we will give a proof in the sequel about this fact, but we should impose some very easy a very easy Chen-Wei theory. So also we need to state some facts about the isomorphism for bundle pairs. That is, if E1 F1 is isomorphic to E2 F2, if and only if first we have an isomorphism from E1 to E2, and second we have this isomorphism must send F1 into F2. So this is a concept of the isomorphism of a bundle pair. And the main theorem concerning the boundary Maslov index is the following. That is, the mu is unique, or is uniquely characterized by the following property. The first one is that if phi is a vector bundle isomorphism, that is if phi from sigma 1 to sigma 2 orientation preserving isomorphism, and which gives an isomorphism phi from E1 to E2, and then we have the Maslov index of E1 and F1 is equal to the boundary Maslov index of E1, of E2, and the image of F1 via phi. This is the first property. And the second is that the direct sum of two bundle pairs must equal to the sum of the corresponding Maslov index. And the last and the third characterization is that if we can decompose sigma into sigma 0, 1 union sigma sigma 0, 1 and sigma 1, 2. So this means that if we write sigma as a cylinder, and we have some very, yeah, and here there is some holes. And then if we decompose it into like it is 0, it is 1, it is 2. So then we get sigma 0, 1 and sigma 1, 2. So it is sigma 0, 2. And we have corresponding bundle pairs. Then we will have like yeah. So then we will have the mu of E of the bundle of the union is equal to mu is equal to the sum of these two boundary Maslov index. So with this, we know that when we are considering a sphere, then we will have this. Like no, we will have like a disk and another disk, and we glue them together, and then the the Maslov index of the whole pair should be the sum of these two, and this will be simply is equal to 2C1E. So we must define the Maslov index of the whole of comparing mass surface without boundary to be twice the first term class. And the last one is the normalization. That is the start of our induction. That is if sigma is a unit disk. The simplest model because it consists only of one boundary, and E is a trivial bundle, E cross C. Then we will have and total real subbundle is given by R times the exponential of ik theta quotient by 2. Then we will obtain that yes, where z is equal to E of I theta is in the boundary. Then the Maslov index of this bundle pair EF is equal to K. Yeah. So this is the start of the induction, and we just and this four property just characterize the whole definition of the Maslov index. And furthermore, we have what happened. And furthermore, we have the following property that will help us in our proof. That is, if E is trivial, so if E is trivial, then we know that mu of the sigma cross Cn and with values in bundle pair with some total real subbundle F is equal to mu of lambda, where lambda is just the given pairs of loops. This is the first one, and the second one is that if d sigma is empty, then mu of E and the empty total real subbundle is 2 times the first term class of E. So to be more explicitly, it is just C1 of E pairs with the, yeah, I think we can say the C of E pairs with the fundamental cycle of sigma, and this belongs to H2 of sigma E. H2 of sigma with values in J. Yeah. So in order to prove this, we need some more preparations because so I think we can firstly, yes, from this we can readily deduce that a corollary that so the two bundle pairs are isomorphic if and only if they have the same boundary Maslov index. And they have the same rank. Because have the same rank. And for each component C of the boundary, we have just the two real vector bundles are isomorphic. And we, so this Maslov index, boundary Maslov index, nearly characterizes all the the isomorphism of the bundle pairs. And now we are going to give a proof of this. So in order to do this, we need some preparations on the parallel path introduction, parallel path induction. I think we can firstly, yeah, I think we can firstly look into the property of the bundle pair. Because it is on the Riemann surface, we have a very good characterization. We know that if we have a complex vector space, then they will be characterized by C1e, C2e, and into Cne, to CRe, where R is the complex rank of E. And when they are all vanish, so they all vanish, we know that the geometrical meaning of a characteristic class is that their existence, like what call this? So yeah, I think you can find in Milner and chapter 12. So like CRE is obstruction of a global frame of non-vanishing sections. And when we can say CR minus 1E will be the obstruction to the existence, no, to a frame of to a non-vanishing section. So one globally non-vanishing section exists, then the CRE must be 0, and so it is existence of two linearly independent everywhere linearly independent sections, and so on. So this tells us that once C2 and CR all vanishes, then we can expect that it has a very good property that nearly we can find a global partial framing of the vector bundle. So that is so we can say a global frame, a partial framing. And here we must impose the fact that we are working with a bundle pair, that is a complex vector bundle with a totally real subbundle. So a partial framing will be considered in the totally real subbundle of E. It's a pair where we have a vector line bundle L and n-1 global sections where S1 and where S1 to Sn-1 nowhere vanishing. Sections of F and L sub line bundle such that F is equal to L direct sum with all the SI. So we know that C will be the complexification of L direct sum with all the complexification of these trivial line bundles. No, it is E, not C. And equipped with such a partial framing, then there exists the global trivialization E. And a smooth function lambda from D sigma to S1 such that phi at the point J of L at the point J is equal to square root of lambda J act on the real line for all J in the boundary, and phi of maps S1 SI into EI, where EI standard basis of Cn and F phi x on Fj is equal to the square root of lambda J x on R and direct sum with R n-1 to the power of n-1. So this is something like a normalization or like a trivialization. And we know that because so topologically we know that sigma is characterized because sigma has boundaries, so it is characterized by the pair sigma with and the D sigma and characterized by H1. So we know that there is a trivialization of E with the trivial bundle because E should at least be characterized by upper 2. So this will always vanish. So we know that E can be trivial, but the bundle pair is non-trivial. So when we have total real subbundle F, then the bundle pair will be characterized only by C H upper 1 of the relative cohomology. So we know that it can be non-trivial. So we have this characterization, and the proof just go as like Well, the proof just like we have we have a boundary. We have a sigma with boundary. This sigma and this is S1. So in order to in order to give a partial framing of F, now we have assigned the partial framing of F. No, I think yes. So if we have such a partial framing, then we can just pick because near any d sigma, we always have one such like a Koga neighborhood. So and when we omit this Koga neighborhood, so when we cancel this Koga neighborhood, then we obtain that sigma should be diffeomorphic to sigma. If this is U epsilon, then cancel with this Koga neighborhood. And in the Koga neighborhood, we have and we have a bundle, and we have a complex vector bundle E to sigma, and then we can use the Koga neighborhood to deform the the vector bundle on D sigma. That is so E restricted to we say that this is sigma 1 equals sigma 1. So E restricted to sigma 1 as a trivialization into sigma 1 times Cn because H2 will vanish. So we have always a trivialization, and we want to deform it into in this small neighborhood so that on the boundary it coincides with the no, what I'm going to say. So okay, so it is easy that we know that E to sigma, and E has always a trivialization to the trivial bundle, but we don't know what the image of F is. So we know we need that the trivial we need that the trivialization must send F to this. Yeah. Yes, we must send F to this, and we have nowhere vanishing, so we have assigned a partial framing to F, so that we must need phi I of L is assigned to this on a boundary, and phi I must map Si, phi must map Si to EI. So in order to do this, we know that yes. So on sigma 1, the restriction is sigma 1 to Cn, and we don't know we map F to what things. Maybe like F is equal to some no, there are no F. No, there are no F. And we know that on the boundary, we just have on the boundary we just have Yes. Uh, so what am I going to say? And we know that the closure of U sigma is equal to D sigma 1 cross 0 to epsilon. This is the definition of the co-neighborhood, and we can just assign the boundary to so we need to glue them together. One is the phi, and another is on the if it is phi 1, and another is on the cylinder. So we need to do the deformation on the cylinder. So phi 2 must map U epsilon. So must map the E restricted to U epsilon to some U epsilon bar cross Cn such that so phi 2 will map L to square root of lambda z times R, and phi 2 must map Si to Ei. Then we just glue them together, and phi 2 is equal to phi 1 when restricted to d sigma 1 cross epsilon, and it is d sigma 1. No, d sigma, and this is d sigma 1. No, they are all d sigma cross the number epsilon. Then we can glue them together, and to obtain a continuous and then a smooth trivialization from E, so that it coincides on this boundary. And then for any boundary, we just do the same thing, like take a co-neighborhood and then deform it. And here we can also pick a co-neighborhood and then deform it, and like that. So we know that oh, so oh yes, yeah. So we know that on the boundary, we know that we always have a loop that is lambda 0, which maps Z to the Fz, and this is in Rn. So this gives a loop in Rn, and we can assign another loop lambda 1z, which is the Lz direct sum with no, it is square root of lambda z and direct sum with Ei, Rei. What is in that? Oh yes, Rei. Yeah, E1 to En and Rei, yes. And this also gives a loop in Rn. and we pick lambda, so that lambda 1z and lambda 2z, lambda 0z has the same Maslov index. Then we just get a homotopy gamma, which maps S1 cross R cross 0, 1 to Rn. So that gamma 0 is lambda 0 and gamma 1 is lambda 1. And we just use the cylinder to realize gamma. That is, we just pick so we just pick an operator U, which is from 0 epsilon cross d sigma to grnc, so that U1z is contract. Yes. Because we have this homotopy, we can then just realize the gamma on the cylinder, and we know that they are all in Rn, so we can derive this Uz such that lambda, I think we should also impose a function, here, such that when we pick it to be epsilon, then this will be epsilon, and no, 1, just 1. We know that the parameter does not contribute to anything. So we can pick this such that for ht we have u, t, and at the point z maps lambda 0 to lambda 1 at the point z. So it should be the converse. Yeah, okay. So it should map it should map lambda 1z to lambda tz. So we know that U1z is identity and U0z is contractible. So this map gives a contractible, so this map gives a homotopy between identity and some contractible loop. So then we can just set psi U, which from U epsilon bar cross Cn to U epsilon bar cross Cn, such that it maps any xv to the pair x and u with values in x and maps on v. Because x is just a cylinder, so we can use one variable for u. And then we have the composition. Because we know that the cylinder is trivial, so we have also a composition. So we also have a trivialization from e to u epsilon to the trivial bundle. And then we just consider the composition. Psi u composite with psi 2. Then we will know that it is also a trivialization. And since it coincides with the so psi 2 and psi 2 must coincide with psi 1 on the psi 2 must coincide with psi 1, so we have in fact we have a global trivialization, and phi 2 is just the trivial of E restricted to the cylinder, so they will coincide. And when we impose this local trivialization by psi u, we know that it coincides. on the boundary d sigma 1 and equals what we want, the partial framing on the boundary. So this is what we want, that a global trivialization phi. So we know that any bundle pair over a compared Riemann surface with boundary can be written as in a uniform way as the bundle pair, which consists of a trivial bundle with this totally real subbundle, and this is our starting point. And then we can apply the so we know that then we just apply sigma equals to d, and then we know that any bundle pair EF is isomorphic to a bundle pair Cn, and with and square root lambda j, I derive sum with REI, and we know that here when we are considering the bundle pair on a disk, we can just replace it as E2 of k theta I, the rotations. So this gives us we have condition 4 in the theorem condition 4 in the theorem completely characterizes the Maslov index on the disk. Then we need to use parallel pan decomposition, which we will introduce next week. Induction. Okay. So that is okay. So what's the question? That is all the content today.